In this video, I'm going to talk about the linear regression model, the common application, how it works, and also how to find the parameters for this model. So let's start. Regression analysis is the collection of statistical tools that can be used to model and explore relationships between variables that are related in a non-deterministic manner. Historically, Sir Francis Galton studied the relationship between the father's height, which we can think of the x variable, and the son's height. We can think of this as the y variable. He found out that if the father's height is above average, then the son's height is also above average, but not as much as the father's height. Okay, and it's the same case when the father's height is below the average, the son's height is also below the average, but not that much below the average. In other words, he found out that the son's height regressed toward the average of the children. So the ones that are above or below the average, they're still above or below the average, but they tend to be closer to the average of the other children. Here's an example case where we may apply the linear regression model. Uh, First, we notice here that we have the data points where the x variable is the revenue and the y variable is the share price. And then we see that there's kind of a pattern here, which is that if the revenue gets larger, the share price tends to get higher as well. If we model it with a line, the line may look like this. You can see that here, if the share price, if the revenue gets larger, then the share price tends to get higher. So this is an example of a regression model. Now, once we have this regression line, we may use the line to predict the share price of a new company. Suppose for the new company, we only have the revenue and we would like to know what would be the share price of that company. So what we can do is that this is the revenue of the company. We use the regression line and then we read the y-axis so we know that the share price of that company would be this much on the y-axis. Another example is when people got a good result when they try to forecast the revenue of an upcoming movie using the predictors, internet searches for the trailers, and also the amount of discussion about the movie in social media. So now that we have seen some applications of the linear regression model, the question is how to find the best line to represent the data points or the instances that we have. In a more technical form, when we define a line that looks like this, we say that we need to determine the parameters here, beta 1, and also the constant beta 0, such that we may define that this line is y equals beta 1 times x plus beta 0. In the example of share price and revenue, it means that we can define share price equals the coefficient beta 1 times the revenue plus the constant of beta 0. So now the problem becomes how to find the value for beta 1 and beta 0. Before finding the parameters beta 0 and beta 1, first we need to have a measure such that we can say, oh, this line is good, this line is bad, and so on, such that we can say, finally, we say that we have found the best line. In order to measure how good or how bad a line is with respect to our data points, we describe the error, which is the difference between the actual observed value of the data point and the predicted value from our regression model. So we say the error is the y actual minus y predicted. Here, the y actual is exactly the y value of the data point, and the y predicted is here. is the predicted value based on our regression line or our regression model. Okay, so the error is defined as the difference between the y actual and the y predicted. This is the y actual, this is the y predicted here exactly on the line. Okay, and then it is obvious that we would like to minimize the error. So the best regression line is the line that can minimize the sum of the errors between all data points and the predicted value based on the regression line. It is more formally described as this. So we would like to minimize the sum squared residual or error. So this is the error for the data point or the instance I, and then we take the square such that we do not have the effect whether the error is negative, is way below the line, or it is positive, it is above the line. Both are errors, so we take the square such that we don't have the effect between plus and minus of the error. Okay, so here we take the sum of all data points or data instances that we have. So, and then we would like to minimize this. And then we define this error further as this, which is the actual y of the data point I, and then this is our prediction. Okay, so our prediction comes from this regression line. So we can say this is beta 1 plus times x plus beta 0, and then if we multiply the minus here to the parenthesis inside, we arrive with this thing here, which is the same with the one with the formula above here. Okay, so this is the function. We call it also the loss function. This is the loss function that we would like to minimize. Once, once we have minimized this loss function, we can also say that we have found the best regression line. Now to find the beta 1 and beta 0 to minimize this loss function, what we're doing is we're taking the first derivative of the loss function with respect to each parameter that we would like to find. So we take the derivative with respect to beta 0. We also take the derivative of the loss function with respect to beta 1, and then set each of this first derivative equals 0. And then we are solving this two equations with respect to beta 0 and then with respect to beta 1. Now solving the first derivative of the loss function with respect to beta 0 equals 0, we get that the beta 0 must be like this. And this is how we may find the optimal beta 0 to define the best linear regression line. Here the y bar is simply the average of all y's in our data set, and then the x bar simply the average of all the x values in our data set for all instances. And then solving the first derivative of the loss function with respect to beta 1 and then set it equal to 0, we get that this is how we the formula that we may use to find the best beta 1. So solving the linear regression model is quite simple. So you can use all the data instances that you have in the data set. You can use these formulas to find the best beta 0 and the best beta 1, and that will define the best regression line. So that's it. Previously, we've seen that in our problem, we only have one independent variable or one x variable only. In reality, we may have more than one independent variables. For example, here we see that we have x1 and x2, and in reality, you may have, let's say, 7 features. So you have x1 up to x7. All the principles are still the same, except that sometimes people call this as a simple linear regression, and this type of linear regression with more than one independent variables is called the multiple linear regression. Okay, so that's the end of this video, and in the next video I'm going to talk about how we may derive the beta 0 and beta 1, which the formula we have seen in the previous slide. So see you in the next video. Thank you.